So to solve this problem, let's just see what is the IRMS and I average for a half wave rectifier. So we already know that for a full wave rectifier, IRMS is I max by root 2 and I average is 2 by pi times I max. Now let's calculate IRMS and I average for half wave. So for the full wave rectifier, the waveform is like this, and for half wave, it is alternate. So of course, the whole time period is from here to here. So this is 0, then this time will be pi by omega, this will be 2 pi by omega. So when we are calculating I average and IRMS and I average, we have to consider one time period. So in one time period, what is the average current and what is the IRMS current? So let's calculate that. So we know I square RMS is given by integral of I square dt by integral of dt, and limits of time is for one time period. Now this represents the area of I square versus time graph. So that you can see is valid only for the up to pi by omega. So limits of time here are from 0 to pi by omega. Because for second half, that integral I square dt will be 0. So that's the numerator, and denominator we have the total time period, so that will be from 0 to 2 pi by omega dt. So we do that. So let's say the sine curve is I max sine omega t. So we put that value here and we solve it, and we get IRMS to be I max by 2. Now similarly, I average is integral I dt by integral dt. So here also, I versus t graph, you can see that that's the area under the sine curve. So the limits should be from 0 to pi by omega. So that will give the area under the curve from 0 to time, total area. Divide by total time, that is 2 pi by omega. So again, if you solve, you are going to get I average to be I max by pi. So these are the values which we get for a half wave rectifier. So we can compare them with this. So average, you can directly see that here you can see average is double, because in one time period you have double the area. So here also you can see average is double of half wave is the average current of full wave rectifier. And IRMS is root 2 times. So whatever is the IRMS here, root 2 times that is IRMS here. So if this is I max by 2, this is I max by 2 into root 2, that is I max by root 2. So we are going to use these formulas in our problem. So this is a problem in T0 hour. It takes T0 hours for current I0 to charge a storage battery. How long will it take to charge such a battery from a mains using a half wave rectifier if effective current is I0? So effective current is IRMS. So when he says to charge a battery, so battery holds charge. So let's say it can hold a charge of Q. So in both the cases, we have to equate the total charge Q which the battery can hold. So if we are supplying the battery the charge, that will be the I average that we are supplying. Sorry, I mean the charge will be I average into time. So that is the charge that's been supplied in T time. So let's start. So for one time period of half wave rectifier, so we already proven before that IRMS is I max by 2. And they have given that this IRMS is I0. So basically what we did is we got the value of I max, that is 2 I0. Now I mean also we saw that is I max by pi. So let's put the value of I max, that is 2 I0. So I mean is 2 I0 by pi. So this is the average current that's been passed in a half wave rectifier. So now let's see Q charge. Let's say the Q charge with DC current is charged in T0 time. So Q is equal to I0 T0 when charging with DC. And when charging with AC also, final charge is Q. So that will be I mean into T time. And this is what we need to find. In how much time it can be charged with AC current. So we put the value of I mean. So the Q is I2 I naught by pi into t. So from 1 and 2, charges are same. So I naught T naught is equal to 2 I naught by pi into t. This gives t is equal to pi T naught by 2. And you can see quite obviously it's going to take longer time than it will take from the direct DC current of I naught. Alright.